Imagine a world where particles behave like waves, cats can be both dead and alive, and objects tunnel through solid walls. Welcome to the world of quantum mechanics. This is not the stuff of science fiction, but a fundamental theory in the realm of physics that revolutionized our understanding of the microscopic world. Born in the early 20th century, quantum mechanics emerged as a radical departure from the classical physics that had dominated scientific thought for centuries. It was a paradigm shift, a new way of looking at the world that challenged long-held notions and opened doors to a reality far removed from our everyday experiences. At its core, quantum mechanics delves into the behavior of particles at the quantum level, a realm so tiny that it's beyond the grasp of classical physics. Here, on the stage of the subatomic, particles don't play by the rules we're accustomed to. They engage in a strange dance, exhibiting behaviors that confound our intuition and defy our classical understanding. Yet, despite its strangeness, quantum mechanics has proven to be a powerful tool for explaining the mysteries of the universe. It's given us a deeper understanding of the nature of light, the structure of atoms, and the fundamental forces that govern the universe. And it's not just about understanding the world around us. The principles of quantum mechanics have been harnessed to create technologies that are transforming our world, from powerful lasers and superconductors to the promise of quantum computing. But quantum mechanics isn't just about particles and waves, atoms and photons. It's also a journey into the heart of reality itself. It's a theory that challenges our notions of certainty and causality, of space and time, and even of the nature of knowledge itself. It's a theory that invites us to question, to wonder, and to explore the deepest mysteries of the cosmos. So buckle up and get ready for a journey into the quantum reality, where the impossible becomes possible. What if I told you that particles could also behave like waves? Welcome to the concept of wave-particle duality. This is one of the most intriguing aspects of quantum mechanics, where particles such as electrons and photons, which we traditionally consider as tiny bits of matter, can also exhibit wave-like behavior. This dual nature is not something we experience in our everyday life, making it a truly quantum phenomenon. But how do we know this? Enter the double-slit experiment, one of the most fascinating experiments in the history of physics. Imagine firing particles like electrons or photons, one at a time, towards a barrier with two slits. If these particles were just particles, we'd expect them to pass through one slit or the other, creating two bands on the detection screen behind the barrier. But that's not what happens. Instead, we see an interference pattern with alternating bands of high and low intensity, just like waves of light or water would produce. This suggests that each particle, even when fired individually, behaves as though it's passing through both slits simultaneously and interfering with itself. This is where it gets even more interesting. If we try to determine which slit the particle goes through by placing detectors at the slits, the interference pattern disappears and we get two bands, as if the particles have stopped behaving like waves and reverted to being particles. This suggests that the very act of observing or measuring forces the particles to choose a path in what is known as the observer effect. This experiment, simple as it may seem, shattered the classical notion of particles and waves being separate entities. It tells us that at the quantum level, particles can behave like waves and vice versa, challenging our understanding of the nature of reality. This duality is a cornerstone in the field of quantum mechanics and has far-reaching implications, from the structure of atoms to the development of quantum computers. So the next time you look at the world around you, remember, what you're seeing might just be the tip of the quantum iceberg. In the quantum world, the more you know about a particle's position, the less you know about its speed. This is Heisenberg's uncertainty principle. Now let's unpack this idea. Imagine you're trying to take a snapshot of a particle in motion. The more you focus on pinning down its exact location, the blurrier your picture becomes of its momentum. Conversely, if you try to capture its momentum, its position becomes indistinct. This isn't due to any technological limitations. It's an inherent aspect of the quantum realm. This principle fundamentally challenges our classical intuition of a deterministic universe and emphasizes the inherent probabilistic nature of quantum systems. Now, let's shift gears to another mind-bending concept, quantum entanglement. Picture a pair of dice. In the classical world, if you roll them, the outcome of one die doesn't affect the other. But in the quantum world, imagine these dice are entangled. No matter how far apart they are, The moment you observe the result of one die, you instantly know the outcome of the other. This instantaneous correlation defies the classical limit of communication speed, the speed of light. This phenomenon, as strange as it may seem, has been confirmed experimentally, even over large distances. It's as if the information between entangled particles is somehow teleporting, sidestepping the constraints of space and time. Einstein famously called it spooky action at a distance. Quantum entanglement has profound implications, particularly in the burgeoning field of quantum computing, where entangled quantum bits or qubits can perform complex calculations at speeds unattainable by classical computers. It also paves the way for quantum cryptography, promising ultra-secure communication channels. Despite its eerie nature and the paradoxes it presents, quantum entanglement is not just a theoretical curiosity, it's a real, observable phenomenon that is pushing the boundaries of our understanding of the universe. Quantum entanglement, defying the constraints of classical communication speed, opens up a realm of possibilities we're only beginning to explore. Ever wondered about being in two places at the same time? In the quantum world, particles can do just that. This mind-bending phenomenon is known as superposition, and it's one of the most intriguing aspects of quantum mechanics. Imagine a cat inside a box. According to classical physics, the cat is either alive or dead. But in the quantum realm, things aren't so straightforward. This is beautifully illustrated through the famous thought experiment of Schrödinger's cat. Here, the cat in the box is both alive and dead until someone opens the box and observes it. Bizarre, isn't it? But that's the essence of superposition. Quantum particles can exist in multiple states at once until they're observed or measured. Now, let's shift gears and talk about another quantum marvel known as quantum tunneling. Picture a ball that you want to roll over a hill. According to classical physics, if the ball doesn't have enough energy, it won't make it over the hill. But in the quantum world, the ball can tunnel through the hill, seemingly defying the laws of physics. This is quantum tunneling in action. Particles can traverse through energy barriers that should, by classical standards, be insurmountable. It's as if the particles are saying, "Hey, you can't tell me what I can't do." Quantum tunneling plays a vital role in many technologies we rely on today. It's at the heart of semiconductors, the backbone of our digital world. Without quantum tunneling, we wouldn't have the microchips that power our computers, smartphones, and so much more. It's also essential in nuclear fusion, the process that powers our sun and other stars. Quantum mechanics, with its superposition and quantum tunneling, challenges our classical understanding of the world. It's like a magic show where particles perform feats that seem impossible. But this isn't magic. It's science, and it's real. Quantum tunneling defies our classical understanding, showing us that there's more to reality than what meets the eye. Quantum mechanics isn't just a fascinating theory, it's a powerhouse for technological innovation. From the infinitesimal realm of subatomic particles, quantum mechanics has surged into the forefront of our technological reality. It's the engine behind innovations that are transforming our world, and it's pushing the boundaries of what we thought was possible. Take quantum computing, for instance. This emerging field harnesses the principles of quantum mechanics to process information. Unlike classical computers that use bits, quantum computers use quantum bits, or qubits. These qubits, thanks to the peculiar nature of superposition, can exist in multiple states simultaneously, exponentially increasing computational capacity. The potential here is enormous, from cracking complex encryption to simulating intricate biological systems. Quantum mechanics also holds the key to understanding nuclear fusion, the process that powers our sun. Quantum tunneling, a phenomenon where particles pass through energy barriers that should be insurmountable according to classical physics, plays a crucial role in enabling the fusion reactions. But quantum mechanics is more than just a tool for technological advancements. It's also a fertile ground for philosophical debates and ongoing research. It's a theory that has challenged our classical intuition and forced us to rethink our understanding of reality. The Copenhagen interpretation, for instance, suggests that the act of observation influences reality. This interpretation, while widely accepted, is still a topic of heated discussion among physicists and philosophers alike. Research into quantum mechanics is far from over. Scientists are tirelessly working to reconcile quantum mechanics with general relativity in a quest for a grand unified theory. And as they delve deeper into the quantum realm, who knows what new phenomena they might uncover. Quantum mechanics, while challenging our classical notions, expands the boundaries of our comprehension and paves the way for a future beyond our wildest imagination. The quantum world is strange, perplexing, and at times downright mind-boggling. But it's also a world of infinite possibilities, and it's this world that's shaping our future.